So it's a great, well, we need an introduction, but it's a great pleasure to invite Avi to give this talk. Avi gave a lecture in Oxford that I was sort of very sorry to miss, about the P versus NP problem, and I'm very happy that he was willing to give us a version of it here today.
Yeah, I was in Oxford in the fall. There was the Clay Foundation had a workshop on the Clay Millennium Program. It's 25 years since. They posted them, and there were talks about each of the 6 open programs, and there were 2 talks about the one that was solved, the Poincare conjecture. Anyway, I'll tell you more or less what we know about this problem. The plan is simple. What they asked us to do is to give a statement of the problem, the meaning, the history, and progress. So I'll do that. I'll tell you about, we didn't solve it yet, right? So various things that came up in the 50 years since it was posted, new direction, notions, connections, techniques. Basically, we uncovered a lot of structure of various types, and I want to tell you about some of these. And the field developed a methodology that I think is very robust and very useful. And you'll see that we know a lot. It will be somewhat dense, this talk. But it's good is that I'll switch context and you can recover if you miss something. There'll be a new topic. But there is much more we don't know. So hopefully all of this will be clear. Let me start. First, I want the statement of the problem. It's a mathematical problem. It can be stated very simply, for example, in this way. You see a map that is given as an input, and we need to decide whether this map can be colored in 3 colors so that bordering countries do not have the same color, like in geography book. So the previous NP question is simply the question of whether this type has a polynomial time algorithm. And it solves it in polynomial time in the size of the map for every map. There are several things to say. I said it, but I'll tell you a few things about the things that appear in this statement. P, the class P, is a class of problems solvable in polynomial time. That's the P part. I note that for this problem, the map coloring problem, there is clearly an exponential time algorithm, right? You can try on coloring. And we ask whether this brute force can be vastly improved. The NP comes from the fact that this problem, map coloring, has a very simple verification procedure. If I gave you a coloring, you can check that it's valid. You can do it in linear time. That's the NP part. The if and only if is sort of amazing because you're asking about the equality of 2 classes of problems and you reduce it to a single one, just a question about a single particular problem, 3 coloring. We'll explain this. And something about how fragile complexity is, if we change the problem to asking, can this map be 2 colors, then there is a really trivial algorithm. Really algorithm. If we ask if there is a 4 color, if you can do it in 4 colors, it's even easier. You don't look at the map and say yes. So somehow 3 is in a sweet spot here. What's the meaning of the problem? So
map you mean two-dimensional, right? Is it two-dimensional that you mean?
2 colors of
No, I mean map.
It doesn't matter. You can assume it's 2 dimensional. Yeah, it's a planar map. I want to give you a very philosophical meaning. We'll get to math afterwards. What is P versus NP about? So here I understood that the astrophysicists don't own a copyright of this system, and I can use it. So imagine this nice guy, the guy that starts a computational problem. And we are interested in two galaxies here. One is the class NP, the class of problems that we want to solve. And a galaxy inside it is all the problems we can solve. And we want the relationship between these two problems. Now, remember that computational problems often come from mathematical problems, scientific problems, intellectual problems. You stare at this picture and you clearly the P versus NP is a question about what's the limit of human knowledge, whether we can know all we want to know. So there's something outrageous here. I said all the problems we want to solve. Maybe we want to solve all the problems that are beyond this. What are the problems we want to solve? I want to give you an answer why it corresponds to this NP, to this class of easily verifiable problems, by giving you sort of a cartoon picture of some professions you are familiar with, like mathematicians. What do mathematicians do? Cartoonishly, we are given a statement and we want to find the proof. What do scientists do? They get data on some phenomena and they want to have a theory explaining it. And what do engineers do? They have constraints on a bunch of resources and they want to design something within the specification, like bridge or phone or whatever. I want to claim that in all these tasks, if you think about them, there are problems certainly we want to solve. But there is a property they have that is clear for all, namely, in all these problems, checking that we found the solution we were looking for. This is easy. If somebody handed out a design or a proof or a theory, we could check. We could refer it and accept or reject or journal. So somehow this property that we can check whether something, a solution is good, I claim is shared by almost anything humans try to do. And these are NP. You know, if we didn't have a criterion to check that we found what we wanted, we probably won't be looked. So clearly in this context, if P was equal NP, then we can cure cancer and solve global warming and warming. And we could automatically solve all these. This is a utopic picture. So that's a very, very high level view of that problem. Let me go to the history of the problem, and again, I'll do it very briefly. It's really about the connections between math and algorithms. They always live together since the dawn of time. We had algorithms, very early on. Even Gaussian elimination was invented by the ancient Egyptians. Now, jumping ahead, Hilbert, a century ago, had a dream, and I think the story is very familiar. He believed that truth in mathematics is the same as provability. Anything that's true, you can prove. And moreover, he believed that if there is a proof, there is a mechanical procedure that will discover it. That was his dream. Of course, we know it was shattered first by Gödel, who refuted the first equality, and then by Turing, who refuted the second. And in order to do that, to do what Turing did, he proved that the halting problem, a problem, is undecidable, does not have an algorithm, does not have a mechanical procedure. He had to define what an algorithm was mathematically. And that was the beginning of computer science, and computer science is a part of math. And people, of course, immediately try to see whether basic problems in math, not the halting problem, which is a problem about algorithms itself, basic problems in math have a finite algorithm to decide basic problems like the word problem in groups and the solution of the Dichotomy equations. And by reducing them, by having an algorithm translate them to the halting problem, it was shown that these are not decidable. You can never understand fully, this word problem or the Dichotomy equation. On the other hand, for other important problems, like first order theory of the real, unrotedness, people did find algorithms. So there was a quest to find algorithms or so they don't exist for various problems. And I think the main issue that people face, not only for this problem, but a lot of other problems that people try to solve with computers, that just the definition of algorithms does not suffice. Having a guarantee that it stops in finite time is just not enough. Some of them were extremely slow. And people started thinking about how to define what efficient algorithms are, what are algorithms that will solve problems in our lifetime. And in the 60s came up with this notion of P, allowing polynomial time in the data type. And at the same time, shortly after, trying to classify these problems that have brute force solutions and efficient verification, encapsulated it in NP, and in particular, the notion of NP-completeness and the question of whether P equals NP, sort of was elucidated in the 60s and 70s. It's a very interesting historical remark that Kurt Gödel in a letter to von Neumann, when von Neumann was already dying of cancer, had many of these ideas, P, NP, and this question formulated in his own language. Von Neumann never answered, and as far as I know, Gödel never pursued it further, but the letter is pretty remarkable. I want to stress that this choice of definition, allowing polynomial time, let's say, as opposed to linear time, something very efficient, was extremely prescient and allowed for the discovery of structure and methodology. And now, of course, people are studying also finer versions of this definition. Okay, so we want to start to understand what is, happening in, between P and NP, and we'll first look inside NP. Later we look outside. So, thanks to this picture, Turing separated the unsolvable from the solvable problems. But NP is very, these are problems solvable in particular in exponential time. And it has these two subgalaxies. One we define, problems that are solvable efficiently, and there are many. And these are problems we find as absolutely or forms, right? And on the other hand, these are the easiest and they are the hardest problems. Problems that are NP-complete, which I'll define next, but they are basically as hard as any problem in NP. And among them is this tree coloring, which is the reason I could define P versus NP the way I did. Proving theorems properly defined, the task we all do, is another NP-complete problem. Result is the first one that was discovered, and so on. So let me just define what this completeness notion is, because I want to talk a bit about it. You can define a partial order on computational problem very simply. A is at most B, which you should read not much harder than B, if an algorithm for B allows you to efficiently solve A. And so a problem is complete in NP if it's in NP, but it's as hard as possible, namely every other problem in NP reduces to it. So it's harder than every other problem. So it's not clear how to get the first one. Once you have the first one, you can. But anyway, people did. I will not talk about it. What is true about them is, they are very convenient. If one is easy, all are easy. If one is hard, all are hard by this reducibility. So we saw two examples, map tree coloring and theorem proving. So one way to read this is reducibility, is saying that if you want to solve, for example, the Riemann hypothesis, you can translate it into a map. Just a statement of the Riemann hypothesis plus let's say, allowing only 100 or 1,000 pages of proof, not more, because nobody will read it. Will give you a map of million countries, then maybe you prefer coloring maps than doing analytic numbers. Anyway, such translations exist. What is interesting is that it looks like they have very particular properties to be the hardest. But in fact, it's ubiquitous. It's all over the map. So we have NP-complete problems, not only in computer science and in math, but in every science, biology, physics, chemistry, economics, and there are thousands and thousands of them. And I think this is a very unique scientific phenomena that a mathematically defined notion, non-trivial, I don't mean like a function, but something like NP-completeness, appears as, in thousands of scientific papers. I don't know any other mathematical notion like it. And if you think about it, there is a reason for this. The reason is important. Computation, the way we look at it today, is that, it's just a process. It's basically the evolution of some environment by a sequence of simple and local rules. And of course, initially, Turing thought of it as the evolution of values of bits in computers, in Turing machines, and then maybe we started thinking about networks of computers. But if you think about it, any scientific theory, when we look at what happens to neurons in the brains or cell in tissues, etc., marketing prices in a market, etc., they evolve essentially in the same way. It's different rules, but they are all evolutions. So because of that, notions of computation, particularly NP-completeness, appear in all these sciences, and this is a source of major collaborations between computer scientists and other scientists integrating computational notions into scientific theory. Okay, so we talked about NP-completeness. I want to talk about the basic question: what can be the answer to the pivot NP question? Well, there's two obvious answers. One is that they are equal, and this I discovered. I mentioned this utopic, but it's not completely right. All crypto systems will die. There will be no privacy or security. You cannot design secret language if P equals M. And this is a subject of basically the theory of algorithms. People invent algorithms for problems for which we didn't have efficient ones. That maybe is the main production of a theory of computation. Another possibility is that they are different, and we'll talk about trying to separate them. How do you prove that something does not have an efficient algorithm? Another part is utilizing hardness. I already told you that hardness is used in cryptography. We'll see other uses of hardness. Somehow, it's clear that having a problem easy is good. But also sometimes having a problem being hard is also good. Basically, this subject of computational complexity and mainly uncovering structural relationship between various types of models or problems and so on. But there is a third possibility. You know what? Some of you do. It can be independent. It's certainly a possibility, it's a mathematical possibility, and not only that, people are looking into it. So one way to get to this is to try to prove weaker statements, like show that weak theories, let's say weak subfragments of arithmetic cannot prove P different than NP. And people are doing this. Is related to a field I will not talk about, the proof complexity, and more related to the distinction not between P and NP, but rather between NP and quantity. We'll assume we are in this world because that's the interesting world in which things happen. Okay, so let's go back to our picture here, and I want to talk about structure. So we saw this easiest and hardest problem sets inside NP. What's happening in the middle? Are there intermediate problems? Well, there are problems like factoring integers for which we don't know. We don't know a polynomial time algorithm, and we don't believe it's NP-complete for some reasons I will not discuss. But what are other problems? Well, we know a few other, 5, 10. On the other hand, we are guaranteed by a simple theorem of Lardner from the 70s that actually if P is different than NP are, and there's an infinite sequence of problems of higher and higher complexity. Every one is super polynomially harder than the other. So why don't we see them? Where are they? There is like dark matter here. Okay, so let's explore this dark matter. Are there problems there or not? And I will tell you about two dichotomies, very basic and general theorem about this dark matter. For this, I have to tell you about a class, a very general class of problems, which you are basically familiar with. These are problems that come in by a set of constraints. Constraints can be varied. So here I have the three coloring of maps as a constraint satisfaction problem. How does it look like? It has a set of variables. They can take some values, in this case, three colors. And I have, for this map, I can write down a system of equations, or in this case, inequalities, which tell you constraints about the values of these variables, right? Adjacent countries should have different values. Another one is a three-sat problem I mentioned, just a Boolean satisfiability of formulas. This is a bunch of constraints saying that the disjunction of three literal variables or complement is true, and you get a list and you need to, ask whether there is a solution. There is a satisfying assignment. Linear equations are an example. Let me focus on linear examples modulo some fixed prime p, 17. So you just get a bunch of equations and you ask, can it be satisfied? Does it have a solution? In this case, I have three lin because I have three variables per equation. You can look at two lin, which will be interesting for a reason, where you have two variables per equation. So all these are computational problems, they are constraint satisfaction problems. So if we generalize this, what is a CSP? It's a problem that is defined by two things, by a relation and its arity. So a relation on k-tuples from and where each variable gets a value from some finite domain, D. So a relation is just a subset of D to the k. And we are getting a bunch of constraints on this variable. And the question is whether they are satisfiable or not. This captures almost all problems we know. Most natural problems come in this form. And some of them are easy, like linear equations, of course, but also two coloring or two satisfiability. And some of them are NP-complete. And a conjecture made in the late 90s by Feder and Vardy was that here there is no dark matter for any of these problems. Each one is either hard or easy. And this was proved after 20-some years and a lot of work. So it is true. There is a dichotomy and there is no, in these problems, there are no dark matter. And it's extremely interesting. One aspect is that not only is it true, but there is a simple criterion. You can look at the relation and tell whether this CSP associated with it is hard or easy.
Then in polynomial time.
In polynomial time, that side of the relation, yeah. And, it mixes a lot of things, not just algorithms and complexity, but there is logic and algebra. It's very interesting. And something quite shocking, I would say. There are very different problems in nature. But nevertheless, at the end of the day, there's only one algorithm for the easy one. And it's just something like Gaussian illumination. And if you don't see it, sometimes it's well hidden, there are really ways of simplifying this and getting it. So all the easy ones are, solved by one algorithm. This is one dichotomy theorem, one big success of the field. There's another one which is even bigger, which is a dichotomy for optimization problems. So I want to tell you about the PCP theorem now, and I'll go back to it later in the talk. Again, we are talking about CSPs, and we talked about decision problems. Can all these constraints be satisfied? by some assignment to the variables or not. But problems appear more often in the, maybe they are not all satisfied, and we want to satisfy as many as possible. Airline schedules, class schedules, I know. You never get everything. You want to ask what's the largest fraction of the constraints which can be satisfied. That's an optimization problem. And the PCP theorem, which is one of the most important ever proved in computational complexity, saying that this problem, let's say you're trying to approximate the number of three such constraints which are satisfiable up to 1%. This is NP-complete. So this was the first time after many decades of optimization where we could argue that some approximation problems are hard. We had for decision problems, we had NP-completeness. Here we had a way to do it in approximation problem. And this was only the beginning. I mean, this theorem is important in many ways that I will not get into. But once you have such a result, you try to get better. What is this percentage and how well can you do for each one? Now, this is a much murkier world. There is no 0-1 answer. In some problems, we knew a factor of 2 approximation. Some problems, we knew a factor of log n approximation. In some, we knew a root n approximation. It's a much more interesting world. And some big achievements in sharpening this result was, for example, you look at the three-sub problem. There are 3 literals in an equation. If you just draw these values as random, you'll succeed, and it's a disjunction. You'll succeed 7/8 of the time. So on average, by a random assignment, you satisfy 7/8 of all constraints. Hastert proved that you cannot do even an epsilon better for any epsilon. It becomes NP-hard. And the same holds for linear equations. You thought that linear equations are easy. Well, it's easy to check if everything is satisfiable. But if I give you something that maybe is unsatisfiable, of course you can draw a random assignment to the variables in ZP. You'll satisfy one fraction, 1/p of them. If you try to do epsilon better, Hastert shows this is NP-hard. And one particular, further pushing of this hardness was a conjecture of Subashkot, which again was extremely prescient and fundamental. He conjectured that even separating for linear equations between doing a little bit better than 1/p, or I promise you that 99% of them are satisfiable, just telling apart this very easy from very hard case, is NP-complete. We don't know this. Iris and her colleagues have a partial result. But we do know that if this is true, then we have a dichotomy theorem for approximation of a very strong form. So this is called the unique games conjecture, if you have this buzzword. Raghavendra showed that if this is true, then we understand the approximability and inapproximability of every optimization program. For every, again, we are talking about constraint satisfaction problem. For everyone, for any relation, there is a constant so that satisfying this constant fraction can be done in polynomial time, but doing any epsilon better is NP-complete. There's a dichotomy of a very fine grain. And here, the algorithm that does it in polynomial time, I mentioned picking at random, but that's not always the best you can do. In fact, the best you can do is, again, guaranteed by one single algorithm. This algorithm is called the sum of squares. Sum of squares algorithm. It's related and evolved from the Hilbert 17th problem about sum of squares, for those who know. But anyway, again, you think there's a bunch of problems of all types. A single algorithm really gets the best you can hope for each one of them. Okay, so we have these dichotomies, we have somewhat of an understanding of the dark matter or its absence in the inside NP. I want to put just one slide about another way in which NP is, the question P versus NP is connected to something that didn't seem related at all in the beginning. It's just one slide. From the 60s and 70s, people started developing probabilistic algorithms. What are they? I'm sure everybody knows. You allow algorithms to toss coin, and you allow them to make a tiny error which you can decrease further. So we know by today, many, many problems for which there are very fast polynomial time algorithms that do what you want, and nevertheless, the best known deterministic solution algorithms require exponential time. There seems to be an exponential gap between what we can do deterministically and what we can do probabilistically. There are many examples, and I mentioned here just some examples which occur in math, mathematical problems, in number theory, algebra, geometry, analysis. I will not read them. And there are many, many more. And the question is, is randomness so powerful? So it was an evolution of several decades, starting with works in cryptography, specifically Blamicalo in the 80s. And today we understand that actually randomness is probably very weak for algorithms. Basically, here's what we know. If something like P different than NP is true, if some hard function exists, then every probabilistic algorithm, every efficient probabilistic algorithm can be replaced by an efficient deterministic one. Randomness buys you nothing. We know very efficient versions today, even of this result. I'm not explaining what this P different than NP equals, but you should think of just hardness result of this same nature. So somehow there is a connection here between the question about proof and computation between P and NP, and something that seemed unrelated. We will go back to this connection later. But basically, this caused a huge evolution of the theory of pseudo-randomness and this paradigm of replacing randomness by just computation and the hard problem. So that's another place where hardness is good. If you have a hard problem, then you don't need randomness. Okay, now I want to go outside NP, and this is the point of view that view NP as proof system. So we want to understand notions of proofs. For millennia, we had the standard notion of the mathematical proof, and trying to understand NP is in particular trying to understand proof. And you'll see lots of different proof systems. So what are essentials of proof systems? This is very basic and everybody agrees on it. We want completeness, namely true claims should have proofs in a proof system. False claims should not have proofs, right? And the third very important ingredient, which is not always in the logic books, but is always present, is that distinguishing these two, namely verifying proofs, must be an easy task, right? If we could not verify proofs that other people write, then there is no use to the proof. Okay, so any proof system has to look like this. So what other proof systems can you have besides me showing you writing a paper about my result? So here is, and here again, efficiency or knowledge time. So what other proof systems are there? So from the 80s, motivated partly by cryptography, the second paper, and group theory, the first paper, people came up with other notions of proof systems. And this is what IP, or probabilistic interactive proof, is. So I want to show you by analogy to NP. In NP, you should think now of proof systems as having two parties, a prover and a verifier. They both know a claim. And The prover wants to convince the verifier. The verifier, of course, doesn't trust the prover. And so he sends an argument, and the verifier, who is an efficient algorithm, should decide to accept or reject, and is always correct, right? The prover cannot convince the verifier of a false claim. This is all proof systems in math are like that, so they are all, languages in NP. In IP, so I'm stressing this. In IP, you allow them to randomize. So you allow the verifier to toss coins, and you allow it to make errors, like in probabilistic algorithms. So here's the verifier, just like before. And the prover is trying to convince the verifier. The verifier will toss coins. The verifier is allowed to make errors. And here I have to stress, this is like sacrilegious for mathematicians, right? Proofs, and we are allowing errors. These errors are errors that occur only with probability that depends on the verifier. It does not depend on, other things. Just a number that can be decreased arbitrarily, for example, by repetition. So if you would decrease it to 1 in a billion, I don't know if your math papers in journals, you probably believe that there is some 1 billion probability that there is a mistake. So anyway, let's study this type of proof system. Another thing you allow in this interactive proofs is interaction. So unlike writing a paper and sending it off, you allow interaction. Like in a class, you can ask questions, or when interacting with a colleague, you can try asking for more details of this lemma. And so what is a class of problems or claims that can be proved in this type of system? You can ask whether this is a reasonable model. It's always a good question. Of course, it's reasonable for the reasons I said, but I want to stress that this is an absolutely revolutionary scientific notion. I have no time in this lecture to talk about impacts of this definition. We'll see some in the development of proof systems, but it's an absolutely fundamental notion. And one particular aspect in which it enriches our life is that this type of proof systems, IP, allow for properties of proofs that normal proof systems don't share. I'm sure many of you heard about zero-knowledge proofs, proofs in which you can convince the other side you prove the Riemann hypothesis, let's say the Clay Foundation, to give you $1 million without giving them a hint about how the proof looked like. But you can convince them that you solve one of the 6 problems without telling them which. And they will still have to give you $1 million. But we complexity theorists went ahead and generalized this even further. Why allow only one prover? How about many provers? Let's say 2 provers. They all share a claim, and now the verifier can interact with both of them. They are not allowed to talk to each other. Maybe they are allowed to develop some strategy in advance, but after the verifier steps in, they cannot talk to each other. So they are trying to convince him. And like before, we want that, they will convince him if the claim is true, and he will reject them and throw them away if the claim is false. So the same, completeness and soundness. What can be proved in this kind of proof system? We go even further. Why allow only probabilistic entities? We have quantum computers. Why not allow quantum proof systems? And they were defined, like for example, when Ivan Haster is IP star, is a quantum version of the one-prover system. And there are multi-prover systems which are also quantum. And we are playing these games and trying to understand the power of these proof systems. And I think one, again, fundamental and very big understanding of the field is that we know exactly the power of all these proof systems in computational terms. Yeah. This is a good question to ask about any model you see, and even if the answer is no, I'm not sure, it doesn't mean you have to stop looking at it. Anyway, we have a full understanding of all these proof systems. I will not talk about all of them. I want to say that, you know, we have these acronyms in theoretical computer science. It's terrible. Instead of dark matter and red giants and black holes and stuff, we have these acronyms. Something should be done about this, maybe it's too late. But all this exact understanding of the power of this proof system also has, each of them has a conceptual meaning. I will give you one of them. IP equals P space, polynomial space, maybe you are not, you have no intuition about this. Can be explained as follows. NP is something about one alternation. There exists a proof that convinces. P space is about many alternations. It's about games like chess. There exists a move I make as white, so that for every move you make as black, there exists a move I make as white, so that blah, 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 blah. At the end, I win. This kind of statement. This is very hard to imagine, I think, for us, how you can efficiently convince somebody else you have it. But this means that if an alien landed here tomorrow claiming they have a winning strategy for white, not just superior power, a winning strategy, right? That's a claim of this nature, then we could test it efficiently. There's an efficient way to verify if indeed they have such a strategy or not. It's a pretty amazing thing given the exponential growth of the game tree. Anyway, so that's the one meaning of the second claim.
What would happen if you ran that against alpha zero? You actually convinced me that alpha zero is not seeing all the way to the bottom.
You would catch it, yeah. You would. There's a way to catch it. If it doesn't have an optimal strategy, and you and I believe it doesn't.
Alpha zero draws. So if he claims
no, but forget draws. That's not the point. That's not the point.
No.
The fact that some humans fail against alpha zero doesn't mean anything. Yeah. So you can test this claim. This player has the win. I want to talk about two of them, this PCP theorem and this last result, which I'll explain. So the first one is the PCP. I mentioned it before in terms of approximation algorithm and hardness of approximation problem. Here's another interpretation of this theorem. I want to define another proof system. It's called probabilistically checkable proof. It's a non-interactive one. It's like NP. So in NP, as before, a prover sends the verifier an argument, and the verifier is deterministic and always correctly decides whether to believe it or not. In PCP, it looks the same, but again, we allow the verifier to be probabilistic and allow it to have some tiny probability of error, but we put a really very severe restriction on this verifier, because we allow it, no matter how long the argument is, the 100-page proof, we allow it to look at 20 bits of this proof only, and use only them to determine whether the proof is correct or not. Okay, so now you have to imagine finding a bug in a 100-page proof by looking at some 20 bits, maybe it's random. But nevertheless, this PCP theorem tells you that it captures everything. Every theorem for which you have a mathematical proof, the proof can be rewritten. In fact, there is an efficient procedure that would take a normal proof and convert it to a PCP in such a way that the verifier can check whether it's correct or not just by this random sampling of a few bits. Somehow this mechanism, which is very complicated, and of course I'm not going to say much about it, I can tell you that some 15 years later, found a very different and more, I would say, appealing and easy to understand proof of the same theorem. Well, this tells you that, you can convert any proof into this form. And what does it tell us? Well, the dream everybody has is that it will allow us to do verification or referring of papers in 2 seconds. Not implemented yet. This is the engine behind the inapproximability results I mentioned before. That's how you get hardness of approximation results. And there are some practical versions of this which go into many cryptographic systems and go into the design of codes, and lots of recent breakthroughs were discussed here in the last few years. So it's an absolutely major event, the PCP theorem. What about the other one I mentioned? So the other one I mentioned is a statement about quantum proof systems. You see this stuff. So what does it say? It says that two-prover proof systems with quantum provers verifiers, on the right-hand side, it says a complexity class, a class of problems. This class of problems is all the recursively enumerable functions. So exactly the class that Turing showed, the class of problems like the halting problem, which in particular includes problems like halting that cannot be decided. So this is an extremely bizarre statement. There are problems that have no algorithms at all, and nevertheless can be verified efficiently if you allow these two provers and you allow them quantum entanglement. Very bizarre statement. And, if you, at this point, I think many people will say, sure, you guys, you invent your own sandboxes and the sand is made of, material from Mars. And, you play with bizarre objects, you get bizarre results. And why do you expect anything else? What's the meaning of this? So this is a complexity theoretic game. But actually, in fact, it's not. It's way beyond the complexity theoretic game. So I'll tell you, and many of you know, this has fundamental consequences for man. This result has implications. It completely resolves central problems in math and theoretical physics. Some of them are here. It refuted the Condon-Bedding conjecture in von Neumann algebra. That's one consequence of this theorem about quantum blah blah. It answered Searson problem about measurements in product spaces. It answered group theory questions, and I should say this was just the beginning. Some of you know it's a new proof technique in mathematics that has such consequences, and you can start playing with it. And as Michael Chapman here and his colleagues did, for example, refuting last year the Alder-Science conjecture, which I don't know, you can say it's in probability or in group theory. Anyway, it's related, for those who know about, to the question of whether there are non-solving proofs, a very fundamental problem. Anyway, this kind of game seems to be, essential for understanding problems more or less of the type, can you approximate an infinite object well by finite objects in various forms. Okay, let me, 10 minutes more, good, that I want to tell you about lower bounds, about trying to separate P and NP. So very structural results now. Let's talk about lower bounds and barriers, which I'll explain. So Turing defined this Turing machine. It's a mathematical object, and now we put math on it, and he developed a lower bound technique, how to prove limitations on the power of such machine. The proof that halting cannot be computed by a finite algorithm, for this he invented this sort of, in some sense, refining Gödel's proof in a very clever way. using basically efficient simulation of Turing machines by universal ones, and then diagonalizing against them. So it's a proof technique to prove hardness. And it was used not just for proving that something cannot be solved in finite time. For example, it was proved one of the earlier papers of complexity theory to prove finite statements. For example, that more resources give you more computational power. For example, things that are unsolvable in some time t and are solvable if you square the time. And so you can separate complexity classes using this technique. And so you can ask yourself, okay, we have a technique, why can't it prove that P is different than? And that's not obvious. It's not obvious. And an answer to this came from Baker, Gill, and Solvay, and they had the idea, again, an idea of Turing, of adding oracles to algorithms. They said that something particular about this technique allows the following. If this technique proves that some two classes are separated, let's say C and D, then it proves that the classes of machines. Then the same will hold if you equip each of these machines with the ability to access some oracle, namely some fixed function, maybe uncomputable, maybe it doesn't matter. But it's a fair game. Both, all sides get to ask the same oracle question. So it's a weakness of the technique that it doesn't notice whether an oracle is added or not. And now, in order to show why it cannot do P and NP, you do something very simple. You invent oracles such that under one of them P equals NP, and under the other P is different than NP. So this technique cannot do it. But this is a barrier. So that's a barrier. And now, once you have a barrier, you can try to overstep it. So one early result, we're taking the same technique, but adding some non-trivial combinatories. These guys managed to prove a linear time version of P versus NP. They showed that linear time, so linear time non-deterministic machines can do more than linear time deterministic machines. So this somehow uses more than this technique. We didn't get much beyond that. That's the strongest we can say about something that looks like sapient. People started looking for different type of techniques. So in the 80s, it was the age of combinatorics. Let's do combinatorics for low bounds. And this comes from a very simple connection between Turing machines and Boolean circuits. Boolean circuits are just, hardware elements that simulate computation by Boolean operation. It's very simple to see that if some function is computed by Turing machines, so Turing machines can handle data of any length. Circuits are hardware of fixed size, so they take n bits. So you can take this function and look at its n projection for any n. If there's an efficient algorithm for this function by Turing machine, let's say in time t, it's very easy to see that there is a circuit of size t of n for every n. So there's a family of circuits that can simulate this Turing machine. The limitation is only that, circuits are finite. So of course, if you manage to, here's a theorem of Shannon, very simple, was realized by others. It's a good thing to do because if you now look at all possible Boolean functions on NB, there are doubly exponentially many of them. Circuits of some size are only exponential many in the size. So this immediately implies that for almost all functions, the circuit needed by them is exponential. So if you could prove that for some function you cannot do better, that will prove a separation, that will prove an exponential low bound on a Turing machine. So the challenge is just to come up, not with a random function, but with some, again, function we want to solve, something that we can describe, not a random function, something we can describe that requires super polynomial size. If we found one, then P is different than NP. And from this, you will see in the next slide, you can apply, you can try to apply, combinatorial arguments. I just want to make sure that you realize the poor status of this question. We don't know a single natural function for which we can prove that the circuit computing is required more than 5n gates. You cannot prove that multiplication is harder than addition, for example, even though I think most people believe that. So what do you do when you cannot solve the general problem? You maim your circuits, you tie their hands behind their back and take out their eyes, and I don't know. So the first big success was on monotone circuits. These are circuits that cannot do negation. It's still interesting because there are many functions we want to compute which are monotone. For example, the clique problem. We have a large graph and we want to know whether there's a large subset in it in which every pair of vertices is connected by an edge. In these papers, which were pretty sophisticated at the time, we understand it better today, exponential lower bound on this type of restricted circuits was given. At the same time, more or less, people studied constant depth circuits. So they have the full AND, OR, and NOT gates, but they're restricted in depth. So that was trying to capture fast parallel computation. You work in layers and you ask what can be done in a constant number of layers. So you can do the OR of many bits or the AND of many bits. But try to do the parity of many bits, just whether there is an odd or even number of ones in the circuit. These results we know today require exponential size. So again, we have exponential size lower bound, but again, restricted circuit. Because parity cannot be done, you ask the natural question. Suppose I add parity as another gate. This has a name again. And again, people found ways to prove exponential lower bounds for other functions. For example, majority function cannot be done by circuits with parity gates or mod P gates. In fact, with mod P, you cannot do mod P. Then you do the next natural thing, which will be easy. You ask, what about mod 6? It's a product of 2 prime. Okay, well, we don't know. We don't know lower bounds for this class. The algebra doesn't work. We don't, as far as we know, NP, all of NP can be simulated by this really simple constant depth circuits of, AND, OR, and mod 6. So, but we can still do something there. It may look pathetic, but I want to end up with the last 2 minutes with another approach to proving lower bound beyond this combinatoric. I just want to prove about to mention the barrier for this type of technique. So the techniques used for solving these problems include what's called approximation method, random restrictions, and various other tools that are quite sophisticated. But as Bowman Woodish, stepped back, like Baker Gill Solver, and said, what are these techniques about and how can we encapsulate them? And they found out that essentially all circuit complexity lower bounds in existence enjoy 2 features, enjoy or suffer from 2 features. One is if they prove some lower bound, let's say for parity, they immediately prove it for half the functions. So that's automatic. And the second is that the hard functions, the functions they declare are hard, for which the lower bound exists, is actually an easy class. You can easily recognize if I give you the truth table. So then they said, maybe very interesting. Can we prove that these do not, will not suffice? And they did condition on an assumption. They showed that if one-way functions exist, so like factories are, assume factories are, then you cannot prove even superpolynomial lower bounds for general circuits that are not handicapped. So we have a very interesting barrier here, and we should overstep it. Yeah, so there's no natural proof that factoring is hard because we assume, if it's easy, it's easy, and if it's hard, and because of its hardness, we cannot have a natural proof for it. So barriers in general in complexity theory are about introspection, looking at the state of art, understanding the techniques we have used so far in order to prove hardness, encapsulating them and trying to understand why they don't suffice. I think this type of introspection exists in parts of mathematics, but I don't know, for example, if people look at all techniques used to prove the Riemann hypothesis and say, look, that's not enough in some sense. Of course, it motivates to find ways around these barriers, and some of these barriers, in particular the natural proof ones, can be translated into logic and actually derive some of the independence results I mentioned in the beginning of previous NP. The last two slides about a different approach to proving lower bound. This is proving lower bound by doing the opposite, the thing we sort of excel in, finding algorithms. Here's an amazing result of William. Amazing, you can say it's pathetic also, but I told you we don't know that NP is not in ACC, this mode 60. But just slightly, n to the low n, non-deterministic algorithm cannot be computed polynomially by the circuit. And here's the approach, which is really interesting. So he suggests the following algorithmic question, which is the satisfiability question we mentioned, for a collection of circuits. So CSAT is a question, I give you a circuit from this class, can you tell me if some input makes the output 1? And it says, okay, obviously we can do it, try all inputs, but that's exponential time. And he said, suppose you have a better algorithm, better by a little bit. Suppose you beat the brute force just by a tiny bit, you shave on polynomial factor. It's really not much. If you do, then you get lower bounds against this plan. And of course, he showed that for ACC circuits, there is such an algorithm. You can test its satisfiability a little better than 2 to the n time, and therefore he gets his lower bound. That's a very different approach. And if you did it for polynomial size circuits, if just testing the satisfiability of a circuit, a normal circuit of size n with n variables, you can test it in 2 to the n over n to the 100 time, then you would have lower bound sort of p different than almost. So the question is whether you can beat up exponential brute force stuff. Another algorithmic question, that's my last slide, that would lead to lower bound is maybe my favorite, and I spent a lot of time on it, is this polynomial identity testing problem. The problem is extremely simple to state. I give you this matrix, it's full of constant 0, 1, and variables, n by n matrix with variables between 1 and n. And they are scattered maybe with repetitions in this table. And what I ask you, so that's called a symbolic matrix, and I ask you whether the determinant of this matrix, which is a polynomial in these variables, is vanishing identically or not. What can we say about this problem? There is this observation of logos, but it's very simple. You don't need logos for that. If you plug in random numbers for the variables, even random numbers from a small one, then it's a perfectly good probabilistic algorithm for the problem, efficient, right? Because determinants can be efficiently computed on numbers. If this was identically 0, if the determinant was identically 0, you'll always get 0. If it was not 0, the chances you land on the variety is negligible. So it's a perfectly good probabilistic algorithm. And we don't have a polynomial time algorithm for this. we said that we believe if we have, for example, if we have a hard problem, then we can de-randomize, but the whole point here is to prove that there is a hard problem, so we cannot assume it. Here's the remarkable result of Cabanet and Pagliazzo. It said that if you found the polynomial time algorithm for this problem only, then you have proved circuit lower bound. Okay, you can stare at it. If you have an algorithm, a deterministic algorithm for this problem, you prove circuit lower bound. So it's the opposite connection. This hardness versus randomness now goes in the other direction. You de-randomize, you prove circuit lower bound. So de-randomization and hardness are coupled very strongly. We don't know this. We don't know how to do this. This comes from, connections. I didn't talk at all about algebraic complexity theory. There's an analogous theory to the Boolean one, P-versus NP. Here there's variant theory, and let me not go into this. And it calls for very interesting connections and approaches to P-versus NP, like the GCT of Marmari and so on, but let me not go there and just conclude. Just trying to understand what this problem means here, what are the classes P and NP, led us to develop this complexity theory and theory of algorithms. And I only showed you just one aspect of it, just time and polynomial time and that. There are many other computational settings. You study algorithms of different types, online algorithms, parallel algorithms, distributed algorithms, quantum algorithms. You study various other resources. You study not just time, but space and energy and memory and communication. And it's a vast field. Moreover, this is a methodology that came with this development of modeling this whole idea of grouping problems in complexity classes and looking for reductions between them and complete problems and so on is very robust, and inventing new models like you saw in the proof system games and so on. There are many, many connections that this brings to math and to other sciences. Some of them we discussed. I think the blue part is the most interesting and important for me, certainly. It's been in it for 45 years and still enjoying myself on a constant basis. And I leave you with the challenge of proving a little hardness. I have a book on complexity theory, which is really for people who really want to read. It's written for easy reading, for people who don't know the field and want to get into it. Thank you.
For this fascinating talk. Questions?
I have a dumb question, just to get a sense of what this is asking. So say the 3-color problem, and you're reducing it down to that. You want a polynomial algorithm. I'm getting the sense that the implication there is that the polynomial, in particular the degree, can't depend on something like the number of countries that intersect. You're looking for a fixed degree polynomial for that algorithm.
Yes, but you can assume that the number of countries neighboring a particular one is at most 5 if you want.
Okay. So you are allowed to basically bound that. Okay.
Yeah, you can.
Okay.
Yeah, there are very simple versions of all these problems. So it doesn't,
That's more simple. Okay.
If P versus NP turned out to be independent, do you think we would choose to take that as an axiom, or P equal to NP as an axiom, which is better, which has more
if they are independent?
which has more?
Yeah, it's a very good question, and I cannot give you a categorical answer. I like the version, and you can see whether it's helpful or not, that says the following, that they are equal. Namely, what does it mean? There is some algorithm that solves recurring in polynomial time, but we just cannot prove that it holds on time, right? What do you do with it? Yeah. No, I think, I don't think they are independent. It's independent. By the way, any prediction you hear from any complexity theory is not based on much. I mean, there is much that happened, but I don't think we have a good understanding of computation, basically. What computers can do.
I mean, what do you do with it? You break every crypto system on earth with that algorithm. So
Yeah, you will know that it will succeed on every, but it will, yes.
it's running and it works.
Yeah,
So
no, so
Couldn't the.
in the utopia sense, yeah, just a second. In the utopia sense, you are absolutely right. You cure cancer and break every crypto system.
without proving it.
Without proving that it does, but everybody will heal. Yeah. Sorry. Was it
I mean, the polynomial degree could be so large that it's not actually useful, right?
Yeah, so I didn't talk about various caveats that, are justified, are legitimate. Like maybe the running time is n to the 1,000, in which case maybe worse than exponential. I don't know if it's, if that's what will happen. Some people believe that, like Doron Zaiberger, that equal NP, but their exponent is 1,000. I don't know if it's. I didn't talk about the fact that many of the problems, they are hard in the worst case, probably, but in everyday instances, they may be easy. Protein folding is NP hard in some formulation, but nature solves it, right? I mean, we fold our protein. Probably our proteins are not worst case, maybe they are best case. They evolved to be, or even satisfiability itself. People have programs that in practice compute satisfiability on instances with millions of variables and constraints. But these, instances come from trying to verify software or hardware. They are very structured instances. And of course, there are all these LLMs, AlphaFold, that folds protein. In other words, we don't understand, that's a theory that's very far from development, understand what are natural instances of problem and algorithms for natural instances of problem. So that's a big open question. Yeah.
What are the obstructions to implementing zero knowledge proofs? Like why
There are
hasn't,
no obstructions. They are
Why-
implemented.
why hasn't it been done for?
Where is Rahul? There's a postdoc here that has a game of. Anyway, people not just implement it. I mean, many of these blockchain protocols for verifying transactions are zero knowledge. I should say the real answer to your question is that the zero knowledge protocols require interaction. Right? These are proofs in the IP model. There is a trick called the Fiat-Shamir trick, which has a way of taking any interactive protocol and makes it non-interactive. It's based on an unproven assumption, and people use it all the time, like they use lots of things that are not verified. But it was recently demonstrated that in some settings, not safe. But anyway, people use this trick and they make things non-interactive, then they become efficient, and they aren't. You don't prove the zero knowledge of your proof of the Riemann hypothesis, but you prove zero knowledge that a value of a polynomial which makes it some value. Yeah.
Last question. I think Avi again.